So one topic we didn't discuss when we were talking about binary trees is how to store them efficiently. So we saw in a couple of the labs um, how to store binary trees using classes, right? But that's not really an efficient use of space since there's a lot of pointers. So we're going to talk today about how to store a binary tree in an array. So just a quick refresher on some of the terminology we used in binary trees. So here's an example of a binary tree using emoji. The depth is the number of links between the root and a specific node. So the depth of the sad face here is 1. The depth of the root is always 0. Depth of the goofy face here is 2 because there's 2 edges from the root. The height is the maximum depth of any tree, try that again. The height is the maximum depth of any node in the tree. So here, the maximum depth is 2, which means that's our height. And a level is the set of nodes at a particular height or depth in the tree. So here, the level 1 is the happy face and the sad face, right? We also had a couple terms that said whether a tree is full or not, whether a tree is complete, right? Complete meaning all of the levels have the maximum number of nodes except possibly the last one, and whether it's perfect. So here, perfect means that it's full and complete, and the last level has exactly 2 to the height leaf nodes. So here the height is 2, and the last level has 4 nodes. So this is an example of a perfect binary tree. One of the nice things to know about a perfect binary tree is that it has exactly 2 to the height plus 1 minus 1 nodes. So here again the height is 2. So this equation says that we should have 2 to the 3 minus 1, so that's 8 minus 1. We should have 7 nodes. And if we look, 1, 2, 3, 4, 5, 6, 7, we have 7 nodes. Right? So that's very cool. That allows us to store all of the nodes of the tree in an array of exactly 2 to the height plus 1 minus 1 nodes, or, elements. So what if we did that? What if we had an array that had that many spaces in it? That means we could store all of the nodes. And if we store them in, remember, breadth first order, right? So the root, and then the first level, then the second level, assuming it's full, then we know that the root has to be at element 0. Level 1 has to be at elements 1 and 2. Level 2 has to be at elements 3, 4, 5, and 6. If we had a level 3, it would be at 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right? So in that way, we can store them all, and if we wanted to, we could reconstruct the tree, right? We could put this guy at the root, and then we know it's 2 children, and we know those 2 children's 4 children, and we know those 4 children's 8 children. Right? So if we add 2 more nodes here, right, we're no longer perfect, but if we had an array that was now 15 instead of 7, we know that if it were perfect, these would be the 1, 2, third, and fourth elements in a perfect binary tree of height 3. So let's put them at the 3rd and 4th location in the array. So that when we want to reconstruct the tree from this array, we still have the root at the first there. The second level contains all of the things in order from left to right. The second level, the third level, which is level 2, has all 4 nodes from left to right. And then this should be level 3. Level 3. Has all 8 nodes from left to right. If they don't exist, that means they're not in the tree. So that way, we can reconstruct the tree. We can say, well, left, right? This is left, left, left child is empty. Left, left, right child is empty. Left, right, left child is crying, laughing face. Left, right, right child is super grinning face, right? And so on. So we can start building out those trees from the array itself. Similarly, if we removed the crying face, we could just remove that element from the array, right? And we could still be able to reconstruct this tree. And here, this guy doesn't have a left child, and correspondingly, that spot in the array is empty. So this isn't very efficient if you have a very tall but skinny tree, right? You could imagine that a tree that was like this would have a lot of empty spaces, right? A lot of these spaces would be empty. But we can still store it in an array, which we can pass around, right? And you'll see that in the lab, right? The whole reason that we want to have this tree stored as an array is so that we can send it to a constructor, and you can reconstruct the tree from the array. All right? So we're not going to get into the details of how to code that because we're giving you that code, right? But you should know how that decoding works, right? And the code is there for you to see, but we already gave it to you. All right?